dear travelers. Welcome back to the Sleepy Circle. When you look up at the night sky on a clear evening, away from city lights, you see stars scattered across the darkness. The Milky Way might stretch overhead like a pale river of light. Planets might gleam steady and bright. If you're lucky, you might catch the soft glow of a distant galaxy through a telescope. It feels like you're seeing the universe laid bare, all of space, spread out for your eyes to witness. But here's the quiet, strange truth. Everything you can see, every star, every galaxy, every glowing nebula, makes up only about 5% of what's actually out there. The rest is invisible, not hidden behind something else, not too faint to detect, but truly invisible, made of things that don't emit light, don't absorb light, and don't interact with light in any way we can observe directly. We know these invisible components exist only because of how they affect the things we can see. It's a bit like looking at the surface of the ocean. You see waves, foam, and reflected sunlight, the bright, active layer. But beneath that surface lies a deep, dark ocean holding far more water than the thin layer of foam on top. The universe is like that. The stars and galaxies are the foam. The invisible ocean beneath is something far stranger. We call the two main parts of this hidden cosmos dark matter and dark energy. Neither name tells you much about what they actually are, because honestly, we don't yet know. The names are placeholders, labels for mysteries we're still working to understand. Let's start with dark matter. In the 1930s, an astronomer named Fritz Zwicky was studying how galaxies in clusters moved. He expected them to drift lazily, held together loosely by the gravity of the stars he could see. Instead, he found that galaxies were whipping around at tremendous speeds, so fast that they should have been flung apart like sparks from a spinning firework. But they weren't flying apart. Something was holding them together. Something with mass, generating gravity, but completely invisible. Decades later, astronomer Vera Rubin studied individual spiral galaxies and found the same problem. Stars at the outer edges of galaxies were moving much faster than they should be, given the amount of visible matter. It was as if each galaxy was embedded in a huge, invisible halo of mass, something that didn't shine, didn't block light, but pulled on stars and gas through gravity alone. Today, we understand that dark matter makes up about 27% of the universe's total mass energy content. That's more than 5 times the amount of ordinary matter, the stuff that makes up stars, planets, and you. We don't know what dark matter is made of. It's not atoms, not protons and electrons, not anything that interacts with the electromagnetic force. It could be exotic particles that barely interact with anything except through gravity. Some candidates have names like WIMPs, weakly interacting massive particles, or axions. But so far, every attempt to catch dark matter particles in detectors here on Earth has come up empty. Yet we see its fingerprints everywhere. On the largest scales, dark matter forms a cosmic web. Vast filaments stretching across hundreds of millions of light years, connecting galaxy clusters like threads in an enormous, invisible spiderweb. Galaxies form and grow along these filaments, sliding into place like beads on strings. Where the filaments intersect, massive galaxy clusters gather, and between them lie enormous voids, nearly empty of galaxies. If you could somehow turn off all the light in the universe and see only the dark matter, you'd still see structure, threads and knots and halos, all invisible but undeniably there. The hidden skeleton that holds the visible universe in place. There's a strange, humbling intimacy to dark matter too. It's not just out there in distant galaxies. It passes through the Earth constantly, and through your body, like a silent breeze made of particles so shy they almost never touch anything at all. Right now, countless dark matter particles are streaming through you, unnoticed, unfelt, utterly indifferent to your existence. If dark matter is strange, dark energy is stranger still. In the 1990s, astronomers were trying to measure how fast the universe's expansion was slowing down. Everyone expected it to be slowing. After all, gravity pulls things together. The initial outward rush from the Big Bang should gradually lose steam like a ball thrown into the air, eventually slowing and falling back down. But when they measured the distances and speeds of distant supernovae, exploding stars that serve as cosmic distance markers, they found something shocking. The expansion wasn't slowing down, it was speeding up. Galaxies far away are moving apart faster and faster, as if something is pushing space itself outward, counteracting gravity's inward pull. We call that something dark energy, and it makes up about 68% of the universe. That means more than 2/3 of everything is this mysterious, invisible pressure accelerating the expansion of space. Dark energy doesn't clump like dark matter. It's spread uniformly throughout space, a kind of gentle, relentless outward push that acts the same everywhere. Imagine space as a stretchy fabric, and dark energy as a force that continuously pulls on the edges, making the fabric expand faster and faster over time. We have no solid idea what dark energy actually is. It might be a property of space itself, a kind of baseline energy that every cubic centimeter of empty space possesses, sometimes called vacuum energy, or the cosmological constant. Or it might be something more dynamic, a field that changes over time, like the Higgs field that gives particles mass. What we do know is that dark energy operates on the grandest scales, and its effects unfold slowly. Over billions of years, it will continue to accelerate the universe's expansion. Eventually, in the deep, distant future, galaxies beyond our local cluster will slip beyond the observable horizon, receding faster than light can travel to reach us. The cosmos will grow lonelier and darker. But that's an unimaginably distant fate. For now, dark energy is simply the quiet, patient force stretching space, making the universe a little larger every moment. Together, dark matter and dark energy make up 95% of the universe. They are the hidden ocean beneath the visible foam. Ordinary matter, the atoms that form stars, planets, mountains, oceans, trees, and every living thing, is the rare exception, not the rule. We are made of the universe's smallest ingredient, a faint trace element in a cosmos dominated by things we cannot see, touch, or fully understand. There's something humbling and beautiful about that. For all our tools, all our telescopes and equations, the universe remains mostly a mystery. The very things that shape its structure and fate are invisible to us. We infer them, map them indirectly, feel their presence through the way light bends and galaxies move, but we cannot hold them or study them directly. Yet that invisibility doesn't make them any less real. Dark matter cradles galaxies. Dark energy stretches the fabric of space. Both are as fundamental to the universe as stars and light, perhaps more so. When you look up at the night sky, remember, you're not seeing most of what's there. You're seeing the bright surface of a much deeper, stranger ocean, one that holds the cosmos together and slowly, patiently pulls it apart. Stars are born, live for millions or billions of years, and eventually die. Most of them die gently, shedding their outer layers and fading quietly into the dark. But the most massive stars, those many times heavier than our sun, die violently in explosions so bright they can briefly outshine entire galaxies. And sometimes what's left behind after that explosion is stranger than almost anything else in the universe. These remnants are called neutron stars, the crushed, collapsed cores of dead, massive stars. They are among the densest, most extreme objects known to exist, and they stretch the laws of physics almost to their breaking point. Imagine a star much larger than the sun, burning through its fuel over millions of years. Deep in its core, fusion reactions create heavier and heavier elements: carbon, oxygen, silicon, and finally iron. Iron is the end of the line. Fusing iron doesn't release energy, it consumes energy. So when a massive star builds up an iron core, it has a problem. For a long time, the outward pressure from fusion has balanced the inward crush of gravity. But now, with fusion unable to continue past iron, that balance breaks. Gravity wins. The core collapses catastrophically. In less than a second, material equivalent to the mass of our sun is squeezed into a space the size of a city. Protons and electrons are forced together, merging into neutrons. The star's outer layers, suddenly unsupported, fall inward and then rebound in a titanic explosion, a supernova. What remains at the center, if the core isn't massive enough to collapse into a black hole, is a neutron star, a city-sized sun. Neutron stars are astonishingly small and astonishingly dense. Imagine taking more than the entire mass of the sun, enough mass to hold 1 million Earths, and compressing it into a sphere about 20 kilometers across. That's roughly the size of a city like Manhattan or central London. A single teaspoon of neutron star material would weigh about 1 billion tons. If you could somehow bring that teaspoon to Earth, it would punch straight through the planet's crust and keep going, an unstoppable clump of hyper-compressed matter. The surface of a neutron star is solid, but not in any familiar sense. It's made of atomic nuclei packed into a crystalline lattice, with a sea of electrons flowing around them. Deeper down, the matter becomes even stranger layers of superfluid neutrons, regions where the usual rules of atomic structure dissolve entirely. Neutron stars spin. Many of them spin very, very fast. When a massive star collapses, it conserves angular momentum. The rotation it had before collapse is concentrated into a much smaller object. Imagine a figure skater pulling in their arms during a spin. The neutron star is like that skater, but taken to an extreme. Some neutron stars rotate hundreds of times per second, their surfaces whipping around at a significant fraction of the speed of light. If a neutron star has strong magnetic fields threading through its poles, it can act like a cosmic lighthouse. As it spins, beams of radiation sweep through space. If one of those beams points toward Earth, we see a pulse of light, once per rotation, regular as clockwork. We call these objects pulsars. The first pulsar was discovered in 1967 by astronomers Jocelyn Bell Burnell and Anthony Hewish. They detected a radio signal that pulsed with incredible regularity, repeating every 1.337 seconds. At first, They half-jokingly called it LGM-1 for Little Green Men, because the signal was so precise it almost seemed artificial. But soon they realized they were seeing something natural, a spinning neutron star, its beacon sweeping across the cosmos. Today, we know of thousands of pulsars, some spinning leisurely, once per second, others rotating hundreds of times per second. The fastest known pulsar, PSRJ 1748-2446 AD, spins 716 times per second. That's faster than a kitchen blender. If neutron stars are extreme, magnetars are even more so. Magnetars are a rare subclass of neutron stars with magnetic fields so intense they defy easy comprehension. A typical neutron star's magnetic field is already trillions of times stronger than Earth's. A magnetar's field is 1,000 times stronger still, around a quadrillion, 10 to the 15th power, times Earth's field. To give you a sense of scale, if a magnetar were located halfway between the Earth and the Moon, its magnetic field would be strong enough to erase every credit card on the planet. If you got too close, say, within 1,000 kilometers, the field would start to distort the electron clouds around atoms in your body. You'd disintegrate at the molecular level before you even felt the gravity. Fortunately, magnetars are very far away. Despite their terrifying magnetic power, magnetars are usually quiet. They sit in space, slowly cooling, their magnetic fields gradually decaying over thousands of years. But occasionally, something shifts in their crust. A starquake, a sudden crack in the ultra-dense material, and the magnetic field lines snap and reconnect, releasing a torrent of X-rays and gamma rays. These bursts can be incredibly bright, even across intergalactic distances. In 2004, a magnetar named SGR 1806-20, located about 50,000 light-years away, released a burst so intense it briefly affected Earth's atmosphere, ionizing particles in the upper layers and disrupting radio communications. For 1/10 of a second, that magnetar, smaller than a city, was brighter in gamma rays than anything else in the sky except the sun. Neutron stars are strange enough, but some physicists have wondered whether, under even more extreme conditions, matter might transform into something even more exotic. Strange matter. In normal matter, atomic nuclei are made of protons and neutrons, which in turn are made of smaller particles called quarks. Protons and neutrons each contain 3 quarks, up and down quarks, held together by the strong force. But there are other types of quarks, including the strange quark. Under normal conditions, strange quarks are unstable and decay quickly. But deep inside a neutron star, where pressures are unimaginably high, some theories suggest that quarks might rearrange into a new, stable form called strange quark matter. In this state, rather than being confined inside individual protons and neutrons, quarks would flow freely in a kind of quark soup, mixing up, down, and strange quarks in a dense, continuous fluid. If strange matter exists, it might be more stable than normal matter. Some speculative ideas even suggest that a neutron star's core could be made entirely of strange quark matter, forming what's called a strange star or quark star. We don't yet know if strange stars exist. Detecting them would be difficult, since they'd look very similar to ordinary neutron stars from the outside. But if they do exist, they'd represent a fundamentally different kind of matter, something that hasn't existed in the universe since the first moments after the Big Bang, when conditions were hot and dense enough for quarks to roam free. Neutron stars and magnetars don't shine like living stars. They don't fuse elements or generate new light. They're remnants, embers left over from a star's violent death, but they can persist for billions of years. Slowly cooling, slowly spinning down, they drift through the galaxy like ancient monuments, relics of stars that died long ago when the universe was younger and the Milky Way looked different. Some neutron stars have companions, other stars, or even planets orbiting them. One famous pulsar, PSRB 1257+12, has at least 3 planets, worlds that somehow survived the supernova that created the pulsar or formed afterward from the debris. Imagine standing on one of these planets if you could. The sky would be dark, lit only by the faint glow of distant stars. But overhead, a tiny, dense point would sweep past. Your sun, a crushed stellar core spinning hundreds of times per second, its beams of radiation slicing through space with mechanical precision. It would be a strange, lonely place, but it would also be a reminder that even in death, stars leave behind wonders, dense, powerful, and utterly unlike anything in our everyday experience. Neutron stars are what happens when a star dies but refuses to quite let go. They are the memory of a star, compressed into something so dense, so small, and so strange that our everyday language barely knows what to do with them. The universe does not waste its stars. Even in their endings, they become some of the strangest things to ever exist. Imagine for a moment a star much larger than our sun. Not the gentle, steady light we're used to, but a young, hot, blue-white sun that burns with restless intensity. It lives fast, fusing its fuel at a furious rate, shining millions of times brighter than our own star, and spending its life in only a few million years instead of billions. For most of its life, the star exists in a kind of quiet balance. Deep in its core, nuclear fusion fuses hydrogen into helium. This fusion releases energy, pushing outward against gravity. Gravity, patient and unrelenting, pulls inward, trying to crush the star into a smaller, denser ball. For millions of years, these two forces hold each other in check. Outward pressure, inward pull, a long, graceful stalemate. As time passes, the core changes. Hydrogen runs low. The star begins fusing helium into heavier elements: carbon, oxygen, neon, magnesium, silicon. Each new stage burns hotter and faster than the last. If you could watch the core's story and fast forward, you'd see layers building up like the rings of an onion. Hydrogen fusing in a shell outside, helium in a deeper layer, heavier elements closer to the center. The star's life is slowly stacking itself for its own ending. At the very center, a new element appears: iron. Iron is different. Fusing it does not release energy to push back against gravity. Instead, it swallows energy like a sponge. When enough iron accumulates in the core, the delicate balance finally breaks. Fusion can no longer hold gravity at bay. The star has run out of its ability to resist its own weight. And then, in a fraction of a second, everything changes. In the final moment before collapse, the star is enormous and luminous. Its outer layers are swollen, perhaps a red supergiant hanging quietly in space. Inside, though, the core is full of tension. Iron atoms are tightly packed. Electrons are squeezed close to protons, held apart only by quantum rules. There is no more room to maneuver. Gravity pushes harder. The core begins to give way. As it collapses, electrons are forced into protons, combining to form neutrons and tiny ghost-like particles called neutrinos. This process, called neutronization, happens on a scale and speed that is hard to fathom. In less than a heartbeat, the core shrinks from the size of the Earth down to something no larger than a city, about 20 kilometers across. The density spikes to unimaginable levels. Matter, which used to be mostly empty space between atoms, is now packed so tightly that the difference between solid and liquid stops making sense. For an instant, the core becomes a kind of immense collapsing hammer, crashing inward under its own weight. Then, suddenly, it stops. That newly formed core is now almost entirely made of neutrons, jammed shoulder to shoulder in a dense nuclear sea. The collapse halts not because gravity has grown weaker, but because another quantum rule steps in. Neutrons, like electrons, resist being forced into the same state. They push back when squeezed too close. This neutron degeneracy pressure, along with the strong nuclear force, acts like an emergency brace, catching the fall of the collapsing star at the last possible moment. The infalling outer layers slam into this abruptly solid core and rebound. A shockwave forms and, helped along by an enormous burst of neutrinos streaming out from the core, the star's outer layers are flung outward in a supernova explosion. For a few weeks, this dying star may shine brighter than all the other stars in its galaxy combined. The explosion hurls heavy elements, carbon, oxygen, silicon, iron, nickel, and more into space, seeding the galaxy with the materials that will someday form planets, rocks, and living bodies like yours. What remains behind, at the center of the expanding cloud of debris, is something small, dark, and ferociously dense: a neutron star. To understand how strange a neutron star is, it helps to lean gently into numbers. Not as a test, but as a way to feel the scale. A typical neutron star might have a mass about 1.4 times that of our Sun. The Sun, in turn, weighs about 330,000 times as much as the Earth. Now imagine compressing all that mass into a sphere roughly 20 kilometers across. A city-sized ball containing more matter than the entire Sun. The density is so extreme that if you could somehow scoop up a teaspoon of neutron star material and bring it back to Earth, that tiny spoonful would weigh around 1 billion tons, comparable to a mountain or more. Of course, there is no way to actually do this. The matter would not remain stable outside the neutron star's gravity and pressure. It would explode outward, like a spring suddenly released. On the surface of a neutron star, the gravity is so intense that if you could stand there, which you can't, you would weigh billions of times what you do on Earth. If you dropped a paperclip from a meter above the surface, it would hit the ground at tremendous speed, gaining enormous energy in just a tiny distance. The escape velocity from the surface, how fast you'd need to travel to break free, is roughly half the speed of light. A neutron star is, in almost every sense, beyond ordinary experience. And yet, it is not theoretical. These objects exist. We detect them. We time their pulses. We feel their gravitational pull in binary systems. They are real, quiet monuments to the violence that created them. If we could somehow slice a neutron star in half like a cosmic fruit and look inside, we'd see layers, each stranger than the last. On the outside is something like a crust. The very top is a thin skin of atomic nuclei and electrons, crushed into a dense solid. This crust might only be about 1 kilometer thick, but it contains more mass than all the stars you can see in the night sky combined. Deeper down, the pressure grows so great that atoms cannot survive as distinct entities. Nuclei pack closer and closer together, forming what some scientists call nuclear pasta, patterns of matter squeezed into bizarre shapes, sheets, rods, and blobs, reminiscent of lasagna, spaghetti, and gnocchi on a subatomic scale. Go deeper still, and even these structures give way. You find a sea of neutrons with a small fraction of protons and electrons, all moving as an exotic superfluid and superconductor. Matter flowing with almost no resistance, carrying currents and magnetic fields through the star's interior. Further inward, near the core, our understanding becomes hazier. The densities here exceed those in atomic nuclei. The usual theories of matter begin to strain. Some studies suggest that, under these extreme pressures, neutrons might partially dissolve into their constituent quarks, forming a dense soup of quark matter. Some models even propose a central core of strange quark matter, where strange quarks join up and down quarks in a new, stable configuration. We cannot yet directly see this interior. We infer it from observations. How massive neutron stars can be before collapsing into black holes. How they respond to tidal forces in neutron star mergers. How their surfaces quake and flicker. The interior of a neutron star remains one of the most mysterious places in all of physics. A region where the familiar rules still apply, but in a way that is stretched and twisted into something profoundly new. When the progenitor star collapsed, it was rotating. All stars spin, some slowly, some rapidly. Conservation of angular momentum, the same principle that makes a spinning ice skater turn faster when they pull in their arms, demands that as the star's radius shrinks, its rotation speeds up. So when a core shrinks from something Earth-sized to something city-sized, its rotation rate can increase enormously. The newborn neutron star spins. It may rotate several times per second, or hundreds of times per second. Its magnetic field, inherited from the original star but intensified by the collapse, can become incredibly strong, trillions of times stronger than Earth's. Charged particles are guided along this intense magnetic field, and beams of radiation, often in radio frequencies, but also X-rays or gamma rays, are emitted from the regions near the magnetic poles. If these beams happen to sweep past Earth as the neutron star spins, we see them as regular pulses of radiation. On, off, tick, tick, tick. These are pulsars rotating neutron stars, acting like cosmic lighthouses. From Earth's perspective, a pulsar is just a point in the sky whose brightness blinks with extraordinary regularity. Some spin once every few seconds. Others, the millisecond pulsars, spin hundreds of times per second. Their pulses so precise that they rival atomic clocks in stability. These spinning remnants can persist for billions of years, gradually slowing down as they radiate away their rotational energy. In the quiet, vast darkness between the stars, pulsars are like distant metronomes, keeping time for a universe that otherwise seems timeless. Most neutron stars are already extreme, but there is a small subset that push one property to the limit: their magnetic field. These are magnetars neutron stars, with magnetic fields up to about 1 quadrillion, 101 quadrillion, to 1 quintillion, 101 quintillion Gauss. Thousands of times stronger than those of ordinary neutron stars, and around a quadrillion times stronger than Earth's field. At such field strengths, normal matter behaves differently. Atoms become elongated, stretched along field lines. Electrons spiral tightly around magnetic field lines, and quantum effects dominate. If a magnetar were placed about halfway between Earth and the Moon, its magnetic field could disrupt electronics and strip information from magnetic storage. Bring it closer, and the field would begin to interfere with the very structure of atoms in your body. Fortunately, all known magnetars are many thousands or tens of thousands of light years away. Most of the time, magnetars are relatively quiet. They rotate, though typically slower than ordinary pulsars, with periods of a few seconds. Their immense magnetic fields slowly decay over thousands of years, releasing energy in the process. Occasionally, this magnetic decay is not smooth. The immense stresses in the star's crust, pulled and twisted by the powerful field, can cause sudden fractures. Starquakes. When the crust cracks and the magnetic field rearranges, energy is released in intense bursts of X-rays and gamma rays. In 2004, a magnetar called SGR 1806-20, located about 50,000 light-years away, produced a flare so powerful that it briefly altered Earth's upper atmosphere, even from that enormous distance. For a tenth of a second, it released more energy than the sun emits in hundreds of thousands of years, in high-energy radiation. Magnetars remind us that even in their afterlives, stars can still produce sudden, startling events, brief, violent flashes against a backdrop of deep time. Strange matter. The deeper possibility. The phrase strange matter sounds like science fiction, but it comes from a very real question. What happens to matter when you compress it beyond the densities found in atomic nuclei? Under normal conditions, protons and neutrons are made of 3 quarks each, combinations of up and down quarks, bound together by the strong nuclear force. But quarks come in more varieties: up, down, charm, strange, top, bottom. Most of these are heavy and unstable, appearing briefly in high-energy collisions and then decaying. In the ultra-dense interior of a neutron star, though, some theorists propose that it might be energetically favorable for matter to transform into a sea of up, down, and strange quarks, forming a new phase called strange quark matter. If strange quark matter is more stable than normal nuclear matter at those densities, then parts of a neutron star's core, or even the entire star, could be made of this exotic material. Such objects are sometimes called strange stars or quark stars. From the outside, a strange star might look very similar to a neutron star. Same general mass, same general size, same intense gravity, and potential for pulsar-like behavior. But inside, instead of a crust over a neutron superfluid, you might have a thin crust sitting on a vast ocean of quark matter, where quarks are not confined into individual protons and neutrons, but move in a shared, degenerate fluid. We don't yet know if strange stars exist. Observations of very massive neutron stars have put constraints on how matter behaves at high densities, and some teams argue that current data hints at the possibility of quark matter in their cores. For now, strange matter remains a hypothesis, a perhaps, a maybe, a distant possibility resting at the boundary of theory and observation. In a way, that uncertainty adds to the deep, calming mystery of neutron stars. We know enough to say they are real. We do not yet know enough to say exactly what they are, all the way down. After the fireworks of a supernova and the drama of its birth, a neutron star's life is mostly about waiting. At first, it is incredibly hot. Temperatures in the interior can reach hundreds of billions of degrees just after formation. But neutron stars are efficient radiators. They cool rapidly at first, shedding heat via neutrinos streaming from the interior and photons from the surface. Within a few million years, they may cool to hundreds of thousands, then tens of thousands of degrees on the surface. From far away, they might look like faint, bluish embers, gradually fading. If the neutron star has a strong magnetic field, it may shine in X-rays for a while, as its magnetic field decays and heats the crust. Magnetars, in particular, can remain X-ray bright for tens of thousands of years. If it has a companion star feeding it matter, it might flare back to life in X-rays and gamma rays, as in falling gas slams into its surface. But eventually, if left alone, most neutron stars become cold, dark, and hard to find. They drift quietly through the galaxy, invisible except for their gravity, and sometimes a faint, residual glow. This is the long afterlife of massive stars. Not fiery and dramatic, but slow, patient, and enduring. From an astronomer's point of view, neutron stars and their relatives are not just curiosities. They are laboratories for physics that we cannot reproduce on Earth. In their interiors, matter is compressed beyond nuclear densities. Their surfaces are testing grounds for gravity, where Newton's laws are no longer enough, and relativity takes over. Their magnetic fields push our understanding of electromagnetism into new regimes. Their rotational speeds allow us to test how stable and precise extreme objects can be. We study how their rotation slows over time. We watch glitches, sudden, tiny spin-ups when the star's crust cracks, and angular momentum is transferred from the superfluid interior to the crust. We observe binary systems where neutron stars orbit other neutron stars, or black holes, and see how their orbits decay as they emit gravitational waves. In 2017, the detection of gravitational waves from merging neutron stars, along with light from the resulting explosion, confirmed that such mergers are factories for heavy elements like gold and platinum. The metals in your jewelry, in your electronics, in your body may well have been forged in collisions between ancient neutron stars. In this way, neutron stars are not just strange relics. They are active participants in the cosmic story, shaping the composition of galaxies and ultimately the chemistry of life. As you lie here, you do not need to imagine every layer of a neutron star or remember every fact. You can let most of it drift away, like starlight fading at dawn. You might just keep one or two images. A star, once huge and bright, collapsing into a city-sized sphere so dense that a teaspoon of it would weigh more than a mountain. A lighthouse in space, spinning hundreds of times per second, sweeping beams across the cosmos with the regularity of a heartbeat. A magnetar, with a magnetic field so strong it could strip information from a credit card across the distance between the Earth and the Moon. Or perhaps a more abstract image, a small, incredibly heavy ember drifting through the galaxy, silent, compact, and unimaginably old. Neutron stars are reminders that the universe can take something familiar a star, a ball of gas shining peacefully in the sky, and transform it into something wholly alien without breaking any of its own rules. Gravity, quantum mechanics, nuclear physics, all the same ingredients we use to describe ordinary matter, combined and intensified until they produce an object that feels almost like a contradiction. And yet, there it is. Not a thought experiment, not a myth, a real thing out there in the dark. Neutron stars live on timescales that make human history feel like a brief whisper. Stars that died before the Earth formed may still be out there, their neutron cores drifting in the galaxy, long after their supernovae faded from view. They will persist for billions, perhaps trillions of years, long after ordinary stars have exhausted their fuel, long after spiral arms have blurred into more diffuse forms, long after most galaxies have used up their gas. They are, in some sense, the enduring punctuation marks at the end of stellar sentences. As you let your eyes close, you can choose to feel small in this story, or you can choose to feel connected. The iron in your blood was forged in earlier generations of stars, some of which may have left behind neutron star remnants. The gold on a ring or in a circuit may have come from neutron stars colliding in a distant galaxy. You are not separate from this story of collapse, compression, and strange matter. You are one of its outcomes. For tonight, you do not need to solve the equations that describe these objects. You do not need to picture every detail of their crusts and cores. You can simply rest with the knowledge that somewhere, far beyond the thin shell of our atmosphere, the ghosts of ancient stars are turning slowly in the dark. They spin on, indifferent and serene, keeping their own time. And here you are, keeping yours. Breath by breath, heartbeat by heartbeat, on a small world warmed by a still living star. Both kinds of time exist together. The quick, human time of days and years, and the deep, stellar time of millions and billions of years. Neutron stars belong mostly to the second kind. But tonight, for a little while, your imagination has brushed against them. Now you can let them drift away again, like distant lights on a very far shore. They will still be there, quietly spinning, long after you have fallen asleep. When we think of planets, we usually imagine them the way we know them in our solar system. Worlds orbiting a star, bathed in sunlight, warmed by a steady stellar fire. Mercury bakes in the sun's glare. Earth spins in the habitable zone, where water can stay liquid. Even distant Neptune, cold and blue, still receives a faint trickle of light from our star. But not all planets have a sun, scattered throughout the galaxy, perhaps in numbers as vast as the stars themselves, are worlds that drift alone through the darkness of interstellar space. They have no parent star, no sunrise, no seasons, just an endless night, lit only by the faint glow of distant starlight. We call them rogue planets, and they are among the strangest, loneliest objects in the universe. Rogue planets aren't born alone. Most likely, they form the same way normal planets do, in the swirling disk of gas and dust around a young star. Gravity pulls material together, building up rocky cores or gas giant spheres. But during the chaotic early years of a planetary system, things can go wrong. Planets migrate. They interact gravitationally, nudging each other into new orbits. Sometimes a planet gets too close to a larger sibling or to the star itself and is flung outward in a gravitational slingshot, cast out of the system entirely. Other times, a young star cluster, a nursery where many stars are born close together, can tear planets away from their parent stars through gravitational tides. The star might keep its grip on some planets, but others slip free, drifting into the space between stars. Once a planet is ejected, it becomes a wanderer. It no longer orbits a star. It travels through the galaxy alone, pulled gently by the overall gravity of the Milky Way, but unbound to any single stellar anchor. Estimates suggest there could be billions, perhaps even trillions, of rogue planets in our galaxy, possibly outnumbering stars. Many are likely gas giants like Jupiter, but there are probably rocky worlds too, Earth-sized or smaller, tumbling silently through the void. Imagine standing on the surface of a rogue planet, if you could. There is no sun in the sky, no bright star to rise and set, no warmth on your face, no blue sky or clouds lit from within by scattered sunlight. Instead, the sky is black, filled with the cold, unchanging light of distant stars. The Milky Way might stretch overhead, a pale band of light, but it provides no heat, no comfort. The surface would be cold, far colder than any place on Earth. Without a star to warm it, a rocky rogue planet's surface would freeze solid, its atmosphere, if it ever had one, condensed into ice or blown away into space. But deep below the surface, things might be different. A planet's interior doesn't cool quickly. Radioactive decay in the core generates heat over billions of years. If a rogue planet is massive enough, and if it has a thick atmosphere to trap that internal heat, it might maintain pockets of warmth beneath an icy crust. Some scientists have speculated that a rogue planet with a thick hydrogen atmosphere and a subsurface ocean could, in theory, remain warm enough for liquid water to exist beneath the ice. A dark, hidden ocean, far from any sun. Life? Probably not. But the possibility, however remote, is a reminder that heat and energy don't have to come from a star. A planet can carry its own warmth with it, a glowing ember drifting through the dark. One of the strangest known rogue planet-like objects has the unwieldy name SIMP J 013656663 plus 0933473, often shortened to SIMP 0136. Discovered in 2016, SIMP 0136 is about 20 light-years from Earth and has a mass roughly 12.7 times that of Jupiter. That puts it on the boundary between a very large planet and a very small brown dwarf, a failed star that never ignited fusion in its core. What makes SIMP 0136 remarkable is its magnetic field. It's about 200 times stronger than Jupiter's, making it one of the most magnetic objects of its type ever detected. And unlike most rogue planets, which are dark and cold, SIMP 0136 glows, not with visible light, but with radio waves. As it spins, its powerful magnetic field generates auroras similar to the northern and southern lights on Earth, but vastly more intense. These auroras emit radio bursts that astronomers can detect from across interstellar distances. Imagine this lonely world, spinning in the dark, wrapped in invisible curtains of light, glowing softly in wavelengths no human eye could see. A faint radio beacon in the emptiness between stars. Closer to home, our own solar system contains a few objects that feel almost as strange as rogue planets, even though they're bound to the sun. Take Hyperion, one of Saturn's moons. Hyperion is shaped like a battered, sponge-like potato, with a surface so porous it resembles pumice stone. Its rotation is chaotic. It tumbles unpredictably as it orbits Saturn, unlike most moons, which keep the same face toward their planet. If you stood on Hyperion, the sky and the ground would spin and lurch in ways that would quickly become disorienting. Then there's Haumea, a dwarf planet in the outer solar system, beyond Neptune. Haumea is shaped like a stretched-out egg, spinning so fast that it completes a full rotation in less than 4 hours, faster than any other known object of its size. The rapid spin has pulled it into an elongated shape, and it even has a ring system, like a miniature, oblong Saturn. These worlds remind us that planets and moons come in stranger varieties than we once imagined. Not all are round and regular. Some tumble, some are battered and porous, some spin so fast they stretch themselves out of shape. Rogue planets, lonely moons and odd dwarf planets all share something in common. They exist in places where we wouldn't expect worlds to be, or in forms we wouldn't expect worlds to take. A rogue planet might drift through the galaxy for billions of years, passing through spiral arms, wandering near star-forming nebulae, perhaps even passing close to other planetary systems, but never settling down, never being captured, just moving on. In that long, slow journey, it sees no dawn, no seasons, no change, just the slow wheeling of the stars, the gradual shift of constellations as it travels tens of thousands of light years, alone in the dark. There is something haunting and beautiful about that. These are worlds without suns, adrift in the quiet immensities of space, silent, cold, and enduring. When we look at images of galaxies, we often see familiar shapes, spirals with graceful arms, elliptical blobs of stars, or irregular clumps scattered across space. These are the standard forms we expect galaxies to take, shaped over billions of years by gravity, rotation, and the occasional collision. But every now and then, astronomers find something that doesn't quite fit the usual patterns. Something so odd, so visually striking, that it looks more like a piece of cosmic art than a natural object. On the largest scales, the universe sculpts itself into structures that are both beautiful and deeply strange, nearly perfect rings of stars, vast bubbles of invisible fire, and enormous voids where almost nothing exists at all. These aren't just oddities, they're clues to the universe's history, traces of ancient events and forces that shape the cosmos into the web of light and darkness we see today. In 1950, astronomer Art Hogue discovered something peculiar while examining photographic plates, a galaxy that looked like a perfect ring. Most spiral galaxies have arms that wind outward from a central bulge, connecting the core to the outer disk in a continuous sweep of stars. But this galaxy, now called Hogue's object, was different. At its center sat a nearly spherical ball of older yellowish stars. Surrounding that core, separated by a wide, dark gap, almost devoid of visible matter, was a near-perfect ring of bright blue stars. It looked less like a natural object and more like a cosmic eye staring back at us. Hogue's object is about 600 million light-years away, in the constellation Serpens. The ring itself is roughly 100,000 light-years in diameter, about the size of the Milky Way. Yet the gap between the core and the ring is so pronounced that it gives the galaxy an eerie, hollow appearance. For decades, astronomers debated how such a structure could form. One possibility is that it's the result of a collision. Perhaps a smaller galaxy passed through the center of a larger disk galaxy long ago, and the gravitational disturbance rippled outward, eventually forming the ring we see today. Another idea is that the ring is simply a very unusual kind of spiral galaxy, where the spiral arms happen to align into a near-circular pattern. We still don't have a definitive answer, but Hogue's object remains one of the most visually striking galaxies we've ever seen. A reminder that galaxies, like planets and stars, can take forms far stranger than our theories initially predicted. In 2010, Astronomers analyzing data from NASA's Fermi Gamma Ray Space Telescope noticed something unexpected. Two enormous structures extending above and below the center of our own Milky Way galaxy. These structures, now called the Fermi bubbles, are roughly 25,000 light-years tall, about half the diameter of the galactic disk itself. They glow not in visible light, but in gamma rays, the highest energy form of light in the universe. If you could somehow see gamma rays with your eyes, the Fermi bubbles would dominate the sky. They'd look like two vast glowing lobes, symmetrically placed on either side of the galactic plane, stretching from the constellation Virgo to the constellation Grus, covering a huge swathe of the heavens. But we can't see gamma rays with our eyes. So for most of human history, we had no idea the Fermi bubbles were there. What are they? Most likely, they're the remnants of a massive outburst from the supermassive black hole at the center of the Milky Way. Today, that black hole, known as Sagittarius A star, is relatively quiet, slowly accreting gas and occasionally flaring up in X-rays. But in the past, perhaps a few million years ago, it may have been far more active. If a large amount of matter fell into the black hole all at once, it would have released enormous amounts of energy, enough to blast jets of particles and radiation outward from the galactic core, perpendicular to the disk. Those jets would have plowed through the thin gas surrounding the galaxy, heating it and stirring it up, creating the structures we see today. The Fermi bubbles are a kind of fossil, a frozen echo of an ancient explosion. They don't change noticeably on human timescales, but they're slowly fading, their energy radiating away into space. They're also a reminder that our own galaxy has a violent past. The Milky Way seems calm and serene from our vantage point on Earth, but the evidence suggests it has gone through dramatic episodes of upheaval and may do so again in the distant future. On even larger scales, the universe is organized into a cosmic web. Galaxies aren't scattered randomly through space. They gather along vast filaments and sheets, like cities clustered along highways and rivers. Between those filaments lie enormous voids, regions where galaxies are rare, and the density of matter is far below average. Most voids are big, but there are a few that are truly enormous. One of the largest and most famous is the Eridanus supervoid, also called the cold spot void. The Eridanus supervoid is about 1.8 billion light-years across. That's roughly 1/10 the diameter of the observable universe. Inside this region, there are far fewer galaxies than average, perhaps 10,000 fewer than would normally be expected in a volume of that size. To give you a sense of scale, if the Milky Way were a grain of sand, the Eridanus supervoid would be a hole in the sand dune the size of a house. The supervoid might not seem strange on its own. After all, the cosmic web naturally produces voids. But what makes the Eridanus supervoid interesting is that it aligns with a puzzling feature in the cosmic microwave background, CMB, a region of the sky where the temperature of the CMB is slightly cooler than average, known as the cold spot. The CMB is the faint, uniform glow of microwave radiation left over from the early universe, about 380,000 years after the Big Bang. It's remarkably smooth. Temperature variations across the sky are tiny, usually less than 0.01%. But the cold spot is a region about 10 degrees across, roughly 20 times the width of the full moon, where the temperature is about 70 microkelvins cooler than the surrounding sky. For years, the cold spot was a mystery. Some scientists wondered if it might be a sign of something exotic, a collision with another universe, a topological defect in space, or some other strange relic from the Big Bang. But in 2015, astronomers discovered the Eridanus supervoid lying along the same line of sight. The idea is that as CMB photons travel through the supervoid, they lose a little energy due to the expansion of space and the lower density of matter in that region. This effect, called the integrated Sachs-Wolf effect, could account for the cold spot's cooler temperature. It's not a perfect explanation. The void may not be quite large enough to fully account for how cold the cold spot is, but it's the best we have right now. And it highlights just how strange and empty some parts of the universe can be. If you could somehow travel to the center of a supervoid, you'd find yourself in a region where galaxies are sparse. Look in any direction, and you'd see only a few scattered lights, separated by vast stretches of darkness. It would feel like being stranded in the middle of a cosmic desert, where the nearest oasis, the nearest galaxy cluster, is hundreds of millions of light years away. Ring galaxies, Fermi bubbles, and supervoids all have something in common. They're shaped by processes that unfold over unimaginably long timescales. Hoag's object may have formed from a collision millions or billions of years ago, and the ring we see today is the slowly fading echo of that event. The Fermi bubbles were likely created by an outburst from the Milky Way's black hole a few million years ago. A brief flash in cosmic time, but still far longer than all of recorded human history. Supervoids like the Eridanus supervoid have existed for billions of years, slowly expanding as the universe expands, their galaxies drifting farther apart as space stretches. These structures don't change on human timescales. From our perspective, they're frozen, static, eternal. But in the universe's long memory, they're dynamic, slowly evolving, growing, fading, reshaping themselves over epochs so vast that entire civilizations could rise and fall 1,000 times and still not witness any noticeable change. Yet they're beautiful. Not because they move or sparkle or flare up, but because they exist at all. Strange, improbable arrangements of matter and energy, carved by gravity and time into forms that surprise us and challenge our understanding. They remind us that the universe is not just a backdrop, not just empty space with stars scattered through it. It's a place of structure and pattern, of beauty that takes millions or billions of years to unfold, and of mysteries that we're only just beginning to unravel. The universe is already vast in your mind, and now we're going to focus on some of its strangest rhythms. High above you, beyond the blue of the daytime sky, beyond the familiar pattern of the Milky Way, the universe is full of clocks. They aren't made of gears or springs. They don't tick in seconds, minutes, or hours. They are made of matter so dense, it almost collapses into nothing. They spin and pulse and flash, sending out beams of radiation with a regularity so precise that compared to them, our best mechanical clocks seem a little messy. We call some of these cosmic clocks pulsars. Others send out quick, bright flashes of radio waves so brief that they're over in less than the blink of an eye. We call those fast radio bursts, or FRBs. In this part of our journey, we'll drift slowly through these strange phenomena, not to solve them, not to worry about them, but simply to watch from a safe distance as the universe reveals some of its most peculiar habits. You don't need to understand every detail. You can just listen to the rhythms, steady pulses, sudden flashes, and the deep quiet in between. City-sized suns that won't quite die. To understand pulsars, it helps to remember how stars live and die. You've already visited the end of a massive star's life. How, when it runs out of fuel in its core, the balance between fusion pushing outward and gravity pulling inward breaks. The core collapses. The outer layers are blown away in a supernova. What's left behind can be a black hole or something else. Sometimes the remnant is a neutron star. This object has more mass than our sun, squeezed into a sphere only about 20 kilometers across, roughly the size of a city. Imagine taking the entire Earth, all of its mountains and oceans and core, and compressing it down into something the size of a small town. Then imagine going even further, compressing the sun instead. That's the kind of density we're talking about. Matter inside a neutron star is so tightly packed that protons and electrons have been crushed into neutrons. A teaspoon of it would weigh more than a mountain. Not a metaphorical mountain, a real one. These stars are not burning through fusion anymore. They're more like hot embers, slowly cooling over millions of years. But some of them have another trick. They spin, and not gently, the way Earth does. Some neutron stars spin dozens of times per second. Some spin hundreds of times per second. As they rotate, they shoot out beams of radiation from their magnetic poles. If those beams happen to sweep across Earth, we see them as regular pulses. Flick, 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 on, off, like a lighthouse on a dark sea, shining periodically across our line of sight. That's why we call them pulsars. When pulsars were first discovered in the 1960s, the signals looked eerily regular. Radio telescopes recorded blips arriving at perfectly spaced intervals. The regularity was so uncanny that the first detected pulsar was jokingly labeled LGM1 for Little Green Men 1 as a placeholder in notes. Of course, it turned out not to be alien communication. It was physics, a rapidly rotating neutron star whose beams of radio waves were intersecting our direction. Once researchers knew what to look for, they found more and more of these pulsing objects. Some pulsars spin slower, with periods of seconds. Others are called millisecond pulsars because they spin hundreds of times each second, like a blender on high speed. If you could stand safely near one, just in imagination, you would see a dark sphere spinning so quickly it would be a blur, with intense beams of radio and X-ray energy shooting from its poles like twin searchlights from far away. With a radio telescope, all we receive is a tiny whisper, pulses that arrive with clock-like precision. Some pulsars are so stable that we can use them like timekeepers to measure tiny changes in space itself, such as the passing of gravitational waves stretching and squeezing the distances between us and them. In that sense, pulsars are not just strange objects. They are instruments the universe has built for us, if we learn how to read them. A planetary system around a corpse. One of the strangest things we found is that even these dead stars can have planets. Around the pulsar, PSRB 1257 plus 12, astronomers discovered planets orbiting a neutron star. These worlds circle a corpse. They may be remnants of a destroyed companion or formed from debris left after the supernova. Imagine what such a place might be like. A sky dominated not by a warm yellow sun, but by a tiny, invisible star that occasionally sweeps beams of high-energy radiation past you. No comfortable, habitable zone as we know it. No gentle, changing seasons. Most likely, these planets are barren and blasted, but their existence tells us something quietly profound. Planetary systems can form in places we never expected. Even from destruction, new orbits can emerge. The universe is patient, and it reuses its material over and over. Even around one of the most extreme objects we know, gravity can still shepherd rocks and dust into new arrangements. If neutron stars are already strange, magnetars are stranger still. A magnetar is a type of neutron star with a magnetic field so strong that it almost defies description. Earth's magnetic field is enough to align compass needles and guide migratory birds. A typical fridge magnet is much stronger than that. Yet a magnetar's field can be billions of times stronger than Earth's and thousands of times stronger than the average neutron stars. If you could somehow bring a magnetar as close as the moon, its field could disrupt the electrons in your body's atoms. At closer ranges, it could erase credit cards, wipe data, and tear apart normal matter. Of course, we are safe. The nearest magnetars are many thousands of light years away. Most of the time, magnetars are quiet, just slowly spinning in the dark. But occasionally, they release flares of X-rays and gamma rays, sudden outbursts when their crust cracks or their field rearranges itself. We've detected some of these flares as bright bursts from across the galaxy. They are like cosmic hiccups, brief, intense, and then gone, leaving behind a slowly cooling remnant that will continue spinning for ages. In the early 2000s, radio astronomers started noticing something odd in their data. They saw single, bright, millisecond-long flashes of radio waves, incredibly brief, incredibly intense, coming from beyond our galaxy. These events were called fast radio bursts, or FRBS. At first, there was some confusion. Were they instrumental glitches? Interference from Earth? Microwave ovens in the observatory lounge? Gradually, as different telescopes in different places picked up similar signals, it became clear FRBs are real cosmic events. Most FRBS last only a few thousandths of a second. In that instant, they can release as much energy in radio wavelengths as the sun emits in days. Some FRBs repeat, like a lighthouse that only switches on every so often. Others have been seen only once. The sources are located by measuring how their radio waves are dispersed as they pass through space. A bit like how light spreads through a prism, but in radio frequencies. That dispersion tells us they're coming from distant galaxies, often billions of light years away. As more FRBs were studied, some began to show patterns. A few repeated with hints of periodicity. Some seem to come from regions where star formation is high, meaning lots of massive stars, and eventually lots of neutron stars and magnetars. In 2020, a breakthrough came closer to home. Astronomers detected a fast radio burst-like signal from inside our own galaxy, coming from a known magnetar. This suggested that at least some FRBs might be produced when magnetars become briefly active, perhaps when their magnetic fields rearrange or their crusts crack. It's likely that FRBs are not all the same. Some may be magnetar flares. Others might come from different compact objects or environments. We are still learning, but we no longer have to imagine entirely unknown, exotic aliens tapping out messages. We can instead picture natural, though extreme, astrophysical processes. cosmic versions of lighting and thunder, briefly lighting up the radio sky. Even neutron stars and magnetars might not be the end of the story. Some physicists have proposed that under even more intense conditions, the neutrons inside a neutron star might break down into their constituent quarks, forming a quark star, an object made of strange up and down quarks in a dense soup. Or others imagine more exotic possibilities, like boson stars, made of hypothetical particles that don't behave like normal matter at all. These ideas are, for now, speculative. We don't yet have clear observational proof that such objects exist, but they remind us that we don't fully understand how matter behaves at the highest densities. Our theories become uncertain. Our equations depend on assumptions we cannot test easily. In a relaxing journey like this, you don't need to wrestle with those uncertainties. You can just note that, even in the realm of what we do know, neutron stars, magnetars, pulsars, FRBs, the universe has already given us more strangeness than we could have expected. Beyond that, it keeps a few secrets to itself. Rhythms across deep time. One of the most calming aspects of these objects is their patience. A pulsar might spin for millions or billions of years, gradually slowing as it radiates energy. A magnetar might flare occasionally, then spend long stretches in relative quiet. FRB sources may switch on and off on timescales we are only beginning to track. From our human perspective, the signals might seem sudden, a burst, a pulse, a flash. But from the viewpoint of the universe, these are just tiny details in a much longer story. Over eons, pulsars will slow until they no longer beam. Their magnetic fields will fade. They will become dark, cold neutron stars, drifting silently in space. New stars will be born. New neutron stars will form, and the cycle will begin again in other regions. The universe keeps time in layers. The flick of a millisecond pulse, the 1,000-year cooling of a magnetar, the million-year drift of a star cluster, the billion-year evolution of galaxies. All of these clocks run together, overlapping in a complex but harmonious way, listening to the faintest ticks. On Earth, large radio telescopes sit quietly, their dishes tilted up at the sky. They look like giant metal flowers, turned toward the night. In the control rooms, computers hum. Very little seems to be happening. But in the data they collect, you can find the signatures of these strange objects, the regular pulses of a distant pulsar, each one like a heartbeat, the single shout of an FRB, arriving unexpectedly in the middle of an otherwise quiet night. Astrophysicists sift through these signals, charting arrival times, measuring dispersion, mapping where in the sky they come from. They are listening to rhythms that no human ear could ever detect directly. Frequencies too low, too high, too faint. Yet, with instruments, we can hear them. In a way, these telescopes turn the entire planet into an ear pressed gently against the universe's chest, feeling for a pulse. As you lie here, you don't need to keep track of the names. Pulsar, magnetar, FRB. You don't need to remember which one spins faster or which one is stronger. You can just hold one quiet image. The universe, vast and dark, filled with tiny, distant lighthouses. Some spin steadily, sweeping their beams in regular circles. Some flicker only once in a great while. Some may be so faint, we'll never notice them at all. And here you are, on a small planet, in a quiet room, letting those rhythms wash past you like waves you cannot see. You are not required to interpret them. You are not required to understand them. You can simply rest, knowing that somewhere, far beyond your window, the universe is keeping its own strange, gentle time. We tend to imagine the universe as a still picture, a photograph of galaxies frozen in place, each a pinprick of light on a vast black canvas. But if you could watch the universe over hundreds of millions of years, speeding up time in your mind like a time lapse, you would see something unexpected. The galaxies would move, not just because space itself is expanding, slowly carrying them apart, but because gravity tugs and pulls on them, creating subtle currents. In this segment, we'll float through these cosmic motions, the strange drifts and giant attractions that shape the large-scale dance of the universe. We'll do it gently, without equations, without sharp turns, just a slow glide through some of the most enormous patterns we've ever detected. First, it helps to separate two ideas. One is expansion, the overall stretching of space itself, like dots on a balloon moving apart as the balloon inflates. The other is peculiar motion, the individual movements of galaxies and clusters due to gravity. On top of that, expansion. If you imagine a river flowing steadily, expansion is the river's current. Peculiar motion is the way individual leaves swirl around rocks, drift into eddies, or are drawn toward whirlpools. On the largest scales, the river of space is flowing outward, carrying galaxies away from one another over billions of years. But superimposed on that, there are subtle currents created by regions of greater mass, clusters, superclusters, and perhaps even stranger structures. We can't watch a galaxy move in real time. The motions are too slow, but by measuring the redshifts of many galaxies and modeling their distribution, astronomers can infer these flows. They can map how galaxies in our cosmic neighborhood are drifting relative to the overall expansion. What they've found is both strange and soothing. We are part of a vast, slow river of galaxies, all gently sliding towards something. When scientists first charted the motions of nearby galaxies, they noticed that many of them, including our own Milky Way, seem to be moving toward a particular region of the sky, in the direction of the constellations Norma and Triangulum Australe. This region was dubbed the Great Attractor. It's not a single object, like a black hole or a lone galaxy. It's more like a region of enhanced mass, clusters of galaxies, dark matter, and hot gas, creating a gravitational well. The trick is that much of this area lies behind the bright band of the Milky Way from our vantage point. Stars, gas, and dust in our own galaxy obscure the view. It's as if we're looking across a crowded room, trying to see a group of people on the other side, but our own friends and furniture are partly in the way. Still, by piecing together data from X-ray observations, which can see hot gas in clusters, and mapping galaxy motions, astronomers have concluded that the Great Attractor region contains multiple massive clusters, such as the Norma cluster, and associated structures. Our local group, the Milky Way, Andromeda, and their small companions, is part of a flow of galaxies sliding slowly in that direction. As mapping improved, scientists realized that the Great Attractor is actually part of a much larger structure. They identified a region of space where galaxy motions all tend to point inward, toward a common center, a vast basin in the gravitational landscape. They named this region Laniakea, a Hawaiian word meaning immense heaven. Laniakea is our home supercluster. It spans about 500 million light-years and contains roughly 100,000 galaxies. Within it, The Milky Way is just one spiral among many, orbiting quietly in one of its filaments. You can picture Laniakea as a vast, shallow bowl in space-time. Galaxies inside it roll gently downhill toward the central region, guided by gravity's subtle pull. Yet even Laniakea is not static. It too is part of larger flows. Beyond it, there are other superclusters, walls and filaments, all connected by the cosmic web of dark matter. The scales are almost beyond comprehension. Light would take hundreds of millions of years to cross Laniakea, and billions more to traverse the structures beyond. And yet, over the universe's history, these structures shift, merge and stretch, slowly redrawing the cosmic map. Farther along in the direction toward which many galaxies are drifting lies another massive structure, the Shapley supercluster. It is one of the most massive concentrations of galaxies in the nearby universe, containing numerous rich clusters. As data accumulated, it appeared that the combined gravitational pull of the Great Attractor region and the Shapley supercluster, along with other large-scale structures, might be contributing to the motion of our local group. It turned out that there isn't just one attractor, but a network of them. Multiple dense regions, each tugging on surrounding galaxies. The universe, on these scales, behaves a bit like a pond with several big stones under the surface. Leaves drift toward different low spots in the gravitational field, their paths shaped by the combined influence of multiple centers. Our Milky Way is one such leaf, moving a few hundred kilometers per second relative to the cosmic microwave background. To us, that speed sounds fast. In cosmic terms, it is gentle. At that rate, it takes millions of years to cover meaningful distances between clusters. In the late 2000s, some studies claim to find evidence for a phenomenon that came to be called dark flow. By analyzing the motions of galaxy clusters relative to the CMB, researchers suggested that there might be a large-scale drift of clusters toward a particular part of the sky, beyond what standard models predicted. If true, this would hint at something even more enormous beyond our observable universe. Perhaps giant structures outside our cosmic horizon gently tugging on us. However, subsequent studies have questioned these findings, suggesting that the apparent dark flow might be due to statistical noise or systematic errors. At present, dark flow remains a topic of debate, not a settled fact. From a soothing perspective, it can be treated as a reminder that there are still edges to our understanding, places where the data are thin and interpretations differ. We do not need to decide tonight whether dark flow is real. We can simply acknowledge that, even in our careful measurements, the universe leaves some things ambiguous. Despite these uncertainties, one picture is clear. On large scales, galaxies are not randomly scattered and stationary. They are part of flows, rivers of matter moving along filaments of the cosmic web toward nodes of higher density. These flows are slow and stately, taking hundreds of millions or billions of years to play out. If you could speed up time and watch the universe from above, you would see galaxies sliding along invisible threads, pooling in clusters, then trickling along towards superclusters, all while the overall fabric of space expands underneath. Some galaxies would merge, creating larger, brighter systems. Others would be flung into more isolated orbits on the outskirts of clusters. Everywhere, gravity is reshaping the landscape, very patiently. There is no hurry. The universe has billions of years to let these motions unfold, bring the focus back to our immediate neighborhood. The local group is a small collection of galaxies bound together by gravity: the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and various smaller dwarf galaxies. Within this group, the Milky Way and Andromeda are moving toward each other. In about 4 billion years, they are expected to collide and merge, forming a new, larger galaxy, sometimes nicknamed Milkdromeda. This sounds dramatic, but the actual process will be slow and mostly empty. Stars are so far apart that very few will actually collide. Instead, orbits will shift. Tidal tails of stars will be drawn out and then settle. Gas clouds may compress, lighting up new waves of star formation. All of this will happen while the entire local group drifts as a unit through Laniakea's gentle gravitational basin, and Laniakea itself participates in larger flows. From our human perspective, the upcoming merger is unimaginably distant in time. Our species may not even exist by then. Earth's continents will have shifted. Its climate will have changed, yet the motions are already in progress. The velocities are measured. The paths have been traced. We are passengers on a galaxy that is both spinning and drifting, part of a quiet, cosmic migration. It is easy to think of the universe as chaotic, random explosions, unpredictable events. But on the largest scales, and over long enough times, there is a deep sense of order and patience. Matter flows from less dense regions to more dense ones. Clusters form at the intersections of filaments. Superclusters emerge from the clustering of clusters. Like rivers seeking the sea, galaxies seek gravitational low points. Given enough time, they gather where the potential wells are deepest. Eventually, as dark energy continues to accelerate expansion, these structures may become gravitational islands. Distant clusters will slip beyond our horizon. Only local structures bound by gravity will remain visible to future observers. For them, the universe may appear smaller and more lonely. We, living now, occupy a special window where we can still see much of the cosmic web, still measure flows and large-scale structure, still sense our place in a much wider context. As you lie here, it might be tempting to feel overwhelmed by these enormous scales, superclusters, great attractors, dark flows. But you don't have to hold the whole map in your mind. You can reduce it to something simpler. Your galaxy is moving, not just in a circle around its center, not just as part of the local group, but also as a small boat on a very wide river of clusters and filaments, all drifting slowly through the deep. There is no urgency in this motion. It does not ask anything of you. It does not require you to act. Whether you are awake or asleep, galaxies will continue to glide along these invisible currents. Superclusters will continue to rearrange themselves on timescales far too long for any human to witness directly. You can let that realization be comforting rather than daunting. The universe is big enough and old enough that it does not mind if you take one night off from solving its mysteries. Picture the Milky Way from far outside, a hazy spiral, its arms full of stars, clusters, and nebulae, a thin halo of dark matter surrounding it like a subtle, invisible cocoon. Now zoom out further. There's the local group, the Milky Way, Andromeda, Triangulum, and their dwarfs, their halos overlapping slightly, moving together toward a shared future. Zoom out again, then Laniakea, our immense home supercluster, like a huge watershed in space, galaxies flowing slowly toward its gravitational center. And beyond that, see the cosmic web, filaments and walls stretching in every direction, dotted with clusters like dewdrops on a spider's web. All of it is in motion. All of it is changing. All of it is very, very patient. And somewhere in one of those spirals, on one dusty arm, on one small planet, a person is lying quietly, listening to this, and letting the gentle knowledge of these motions lull them towards sleep. You don't need to travel the universe to be part of it. You already are. The same gravity that guides galaxies also holds you to your bed. The same physics that shapes superclusters also shapes the warm air in your lungs. You can let that thought cradle you, like a current so gentle you barely feel it. The universe is drifting, your galaxy is drifting, and for now, you are drifting too. Toward rest, toward stillness, toward dreams. If you've ever looked at an old family photo, one that was taken before you were born, you know a special kind of feeling. You see people you recognize, only younger. You see places that haven't yet changed. You see a world that you know leads to you, even though you are not in the frame. The universe has something like that too. A picture taken when it was very young. A faint, almost uniform glow that fills all of space, all the time. It is not a photograph on paper. It is made of light itself. Ancient light that has been traveling for more than 13 billion years. We call it the cosmic microwave background, or CMB. We can't see it with our eyes. It's too faint and too cool. But sensitive instruments, high above Earth's atmosphere, can detect its soft radiation coming from every direction in the sky. This glow is one of the strangest and yet most quietly beautiful things in the universe. It is the afterglow of the universe's own beginning. Tonight, we're going to lie back, relax, and drift into that faint light. We'll explore how smooth it is, how slightly flawed, and what those flaws might be telling us. You don't need to follow the technical details. You can just let the images settle lightly in your mind, like a very old, very thin blanket being gently wrapped around everything. To understand the CMB, imagine rewinding the cosmic clock. Galaxies unwind and disappear. Stars reverse their aging, growing younger and hotter until they dissolve back into diffuse gas. Planets unform, breaking up into the dust and gas that once made them. Keep rewinding, billions of years, until you reach a time when there were no galaxies at all, no stars, no planets, only a glowing, hot, dense fog of matter and light. Around 380,000 years after the Big Bang, the universe cooled just enough that electrons and protons could combine to form neutral atoms. Before that, the free electrons scattered light in every direction, making the cosmos opaque, like the inside of a glowing cloud. When atoms formed, the fog thinned. Light was suddenly free to travel. Photons, the particles of light, set off in straight lines from that moment, moving outward in all directions, carrying with them a snapshot of the universe as it was then, a nearly uniform sea of matter with tiny, tiny ripples. Those photons are still traveling. As the universe has expanded, they have been stretched, their wavelengths lengthened, their energy cooled. What was once a dazzling glare is now a faint microwave glow, the CMB. It is the universe's baby picture, not of one star or one galaxy, but of everything, almost perfectly smooth. When we first detect the CMB, it seemed astonishingly smooth. Same temperature everywhere, no matter where we looked. At first glance, that might not sound strange, but consider what it means. Regions of the sky that, in the early universe, were so far apart that light had not yet had time to travel. Between them had almost exactly the same temperature. It was as if the entire universe had agreed on a temperature before there was time to share the news. This was a clue that something like cosmic inflation, an extremely rapid early expansion, had happened, smoothing everything out. Later, more sensitive instruments like the COBE, WMAP, and Planck satellites revealed that the CMB is not perfectly smooth after all. There are tiny variations in temperature, typically only about 1 part in 100,000. These slight differences are crucial. Denser regions show up as slightly warmer or cooler patches. Over billions of years, gravity amplified those little wrinkles, turning them into galaxies, clusters, and cosmic filaments. You can think of the CMB as a still pond with barely noticeable ripples. Those ripples are the seeds from which the entire cosmic structure grew. A flaw in the baby picture. When scientists mapped the whole CMB sky with high resolution, they noticed something odd. Amid the tiny, random-looking fluctuations, there was a region, about 10 degrees across, in the constellation Eridanus, that was significantly colder than the average. Colder not by a huge amount, but more than would be expected from random chance alone. If the CMB were perfectly Gaussian and statistically uniform, they called it the CMB cold spot. Imagine a perfectly baked cookie, almost the same thickness everywhere, but with one small region that dips just a bit lower. The cold spot is like that, a blemish in the otherwise smooth pattern. Why is it there? For years, this question has gently nagged at cosmologists. It's not a crisis, but it is a curiosity. The universe's baby picture, nearly perfect, has one noticeable flaw, and we would like to know why. One favored explanation involves something called a supervoid. Space is not evenly filled with galaxies. There are regions packed with galaxy clusters, and there are regions with very little in them at all. The underdense areas are called voids, large, almost empty bubbles in the cosmic web. Now, imagine CMB photons traveling from the last scattering surface, the surface of that early fog, toward us. On their way, some of them pass through a large void, because the void has less matter than average. Its gravitational potential is different. The light passing through can lose a tiny bit of energy in a way that is not perfectly balanced. This effect is known as the integrated Sachs-Wolfe effect. In a universe where dark energy is causing the expansion to accelerate, the gravitational wells and hills of space change over time. As photons climb out of these evolving potentials, they can end up a little cooler or a little warmer than they started. So, if there happens to be a very large void along one line of sight, it can leave a small cold imprint on the CMB. Several studies have indeed found evidence of a giant underdense region, the Eridanus supervoid, aligned with the cold spot. It stretches something like 1.8 billion light-years across, with fewer galaxies than average. Light crossing that region travels through a slightly thinner part of the universe, and that can nudge its temperature downward. However, as measurements improved, some analyses suggested that the void we see may not be quite deep or large enough to account for the entire anomaly. Some studies using gravitational lensing, how much the void bends light, suggest that the void's effect on the CMB might be too small to fully explain the cold spot's properties within our standard cosmological model. Different teams reach slightly different conclusions. Some say the supervoid explanation is plausible and likely. Others argue that the cold spot might still be, at least in part, a statistical fluke, an unlikely patch that nevertheless appears once in a while in a random field. There is also the possibility, though less favored, that the cold spot could hint at something more exotic, a relic from early universe physics we don't fully understand. But for now, most cosmologists tend to favor the gentlest answers, a combination of normal fluctuations plus the cooling effect of a large void. The CMB is still an excellent match to our standard cosmological picture. The cold spot is an interesting wrinkle, not a fatal tear. If you could see the CMB the way satellites see it, you would see the entire sky covered in a mottled pattern of tiny hot and cold spots, reds and blues, just a little brighter or a little dimmer than average. The cold spot is just one feature in that map. There are many others, regions slightly hotter, regions slightly cooler. Together, they form the fingerprint of the early universe. From those small differences, we can infer the total amount of matter and dark matter, the density of baryons, and even the geometry of space itself. It's remarkable that from such faint ripples, we can reconstruct so much. The CMB has become a kind of quiet foundation for modern cosmology, a reference frame against which we calibrate our models. And yet, even within that foundation, there are details we're still smoothing out. The cold spot, some slight asymmetries, a few higher than expected alignments. Nothing that breaks the story, just little reminders that we do not understand everything yet. A very old glow around you. It can be easy to think of the CMB as something abstract, something only telescopes see. But that ancient light is passing through you right now. The photons are weak and rare at any one place and moment, but they are there. A background of microwaves that suffuses all of space at a temperature of about 2.7 degrees above absolute zero. The reason your room is not that cold is because other sources of energy dominate. The warmth of your body, the heat of your surroundings, the sunlight stored in walls and furniture. But beneath all of that, like a faint, omnipresent hum, is the cosmic background, light that set out on its journey long before Earth formed, light that has crossed most of the visible universe, slipping by galaxies and voids, superclusters and dark matter filaments. When it brushes past you, it carries in its pattern the memory of a time when there were no stars at all, only a hot, nearly uniform plasma. That is, in a very literal sense, the oldest light you will ever be touched by. Being small in a very old story, contemplating the CMB and the cold spot can make us feel very small. We are tiny creatures on a tiny planet, mapping temperature differences of millionths of a degree in a glow that fills all of space. We argue over whether a particular patch is colder than it should be by a fraction that we can only see with elaborate instruments and careful statistics. Yet, this is also a testament to how far we've come. From a species that once looked at the sky and saw only myths and omens, to one that can detect subtle patterns in leftover light from the beginning of time. That is a long journey. And the work is not done. Researchers still improve their maps, refine their models, and test whether features like the cold spot are anomalies, hints, or simply coincidences in a random field. The universe, for its part, is not in a hurry to reveal its secrets. It has billions of years to wait. We, who live for a handful of decades, glimpse only a tiny slice. We see the baby picture of the universe long after the baby has grown up. As you lie here now, you might imagine that ancient glow as a very old, very thin blanket draped over everything. It reaches far beyond the walls of your room, beyond Earth's atmosphere, beyond the solar system, out past the edge of our galaxy, and across all of intergalactic space. It does not care where galaxies are or where stars burn. It simply fills the cosmos, almost uniform, with just enough texture to remind us of the universe's restless past. The cold spot is a slightly cooler patch in that blanket, perhaps caused by a vast underdensity, the Eridanus supervoid, curving space-time just enough to drain a little extra energy from passing light. Perhaps partly a statistical quirk, perhaps a hint that our models still have room to grow. But whatever its ultimate explanation, the cold spot does not make the blanket any less comforting. If anything, it adds character, a small imperfection that makes the whole picture feel more real. You can imagine yourself wrapped in that blanket of ancient light, your worries and thoughts slowing down as you realize how long this glow has lasted and how gently it changes. The universe carries its past with it, in light and in structure. You carry your own past in memories and in your body. Tonight, both can rest. We have wandered through a universe of oddities, invisible dark matter scaffolding galaxies, dark energy stretching space, neutron stars squeezed into city-sized spheres, magnetars flaring like silent storms, rogue planets drifting between the stars, ring galaxies and supervoids sculpting space on unimaginable scales, pulsars ticking, fast radio bursts flashing, galaxies drifting toward attractors, and an ancient glow wrapping it all in faint microwave light. All of these are strange. They defy our everyday sense of what is normal. They stretch our imagination. They invite awe. And yet, there is something even stranger, hiding in plain sight. You, or more precisely, the fact that there is anything at all in this universe that can notice the universe, that can feel, that can ask questions, that can lie awake and listen to a story about it all. In this last segment, we gently turn inward, without becoming heavy or philosophical. We simply recognize that in a cosmos filled with wild objects and vast structures, perhaps the most unusual thing is that, in at least one place, matter has arranged itself into mindful, curious beings. You don't have to solve this mystery. You can just let it wash over you as a quiet, comforting strangeness, stardust that can wonder. You are made of ordinary matter, protons, neutrons, electrons, hydrogen, carbon, nitrogen, oxygen, iron, and more. The atoms in your body were forged in the earliest moments after the Big Bang, in the cores of stars, and in the explosions of supernovae and the mergers of dense stellar remnants. The hydrogen in the water inside your cells may date back to the first few minutes of the universe's existence. The carbon in your muscles and the calcium in your bones were cooked inside stars that lived and died long before the sun formed. When those stars exploded, they seeded space with heavy elements, which later collected into clouds, which later formed our solar system, which later cooled, which later gave rise to chemistry, and then to life, and eventually to you. You are, in a very real way, the universe remembering itself. The strangest thing is not that matter can become dense, or form arcs, or glow in microwaves. It's that some of that matter has become aware enough to ask where it came from. From the outside, if someone could look at the universe as a whole, your body would be a microscopic speck on a speck. The Earth is small compared to the sun. The Sun is tiny compared to the Milky Way. The Milky Way is one galaxy among hundreds of billions in the observable universe. Our entire observable region is likely only a patch of something even larger. Within that vastness, the total amount of matter arranged into living nervous systems is minuscule, and the portion of that matter arranged into brains capable of abstract thought, memory, and self-awareness is smaller still. Yet, here you are. Your brain, about 1.5 kilograms of soft tissue, has woven from its activity a sense of self, a sense of world, and the ability to follow this slow, gentle narrative. Millions of neurons are firing in quiet patterns right now, some responding to the sound or text of this script, others regulating your breathing, others generating the feeling of tiredness, comfort, or drifting. The same laws of physics that govern quarks and galaxies are acting in those cells. But at this scale, they give rise to something new: experience. No one fully understands how. We can map activity, trace circuits, identify chemicals and signals. But the fact that it feels like something to be you, that inner glow of awareness, is still a deep puzzle. In a universe full of strangeness, consciousness may be the strangest of all. It took the universe billions of years to produce beings who could think about it. Stars had to form and die over and over to enrich space with heavier elements. Planets had to accrete and cool. Stable environments had to persist long enough for life to arise. Evolution had to unfold across countless generations. Each step could have gone differently. Your particular existence is balanced on a vast number of tiny contingencies. An uncountable web of if this, then that, spreading back into deep time. The universe had enough time and enough patience to explore the possibility of consciousness, of organisms that can not only react, but also reflect, not only survive, but also tell stories. In the grand scheme, this is a brief experiment. We don't know how long it will last, but it is happening now. You are part of it. Outside, galaxies continue their slow journeys. Dark matter halos continue to cradle them. The cosmic microwave background continues to cool very slightly as space expands. Stars are born in distant nebulae. Planets circle their suns. Somewhere, perhaps, other minds look up and wonder. Here, you are part of the same universe, but you do not have to move with it. You can allow yourself to be still. Your nervous system knows how to fall asleep. It has done it many times before. You don't need to manage the process. You just need to get out of its way. Let your jaw loosen. Let your shoulders drop. Let your hands unclench. Let the muscles around your eyes soften. Feel the support beneath you, holding your weight. Feel the air entering and leaving your lungs effortlessly. The universe has been here for billions of years without you. It will continue for billions of years more after you. For this small interval, you get to be a conscious part of it. That is enough. You can let yourself drift, the way a leaf drifts on a calm pond, carried by currents it does not need to understand. If sleep comes, let it. If it takes a while, that's okay too. You are already resting. In a universe filled with strange and beautiful things, here is one more. A mind, gently quieting, choosing, for a little while, to step out of the whirlwind of thought and simply be under the same ancient stars, within the same patient cosmos. And if you'd like to listen to more such documentaries, subscribe and hype this video so that it reaches even more curious minds. Good night, dear traveler, and keep looking up.